Okay, so today we're honored to interview one of our pioneers in the Magnetic Society in Taiwan, Professor Qingrui Zhang. And he received his PhD from University of California, San Diego, and before that he got his bachelor degree from here, National Taiwan University. And his academic career has been working on micromagnetics, spintronics, and 2D magnetism. And he's also one of the earliest, pioneers in establishing IEEE Magnetic Society in Taiwan.
Yeah.
And also he's our IEEE fellow, and he's been the vice president of National Taiwan University. So today I'm very honored to interview you, and I'd like to start with your educational background. Like, how did you get into the field of physics, and why did you go to United States for your PhD degree?
Okay, first thanks, Professor Bai for very detailed introduction. Actually, yeah, actually when I was very young, probably in primary or junior high school, I didn't plan to be a scientist. I tried to be a archaeologist at that time because I read a lot of novels related to the, some kind of the history and all other things. That actually attracted me a lot when I was very, very young. However, after junior high and the senior high, because actually we studied the maths and the physics, and yeah, I think I'm quite good on that actually at that time. And so it's quite natural actually in Taiwan background. Then you will move to that direction because all the environment and your family, your friends think to study the basic science. At that time actually there is no semiconductor industry in Taiwan. So I naturally I went to physics department of National Taiwan University because actually at that time is a top choice actually for the senior high school student if you want to study fundamental science. And yeah, you just remind me a long time ago history. But anyway, when I was in my undergraduate, after I studied the quantum physics, it's really opened my mind and to find another way to see this universe. But when I graduate, I suddenly realized I cannot find a job in Taiwan because actually there is no any industry at that time in Taiwan. Back to 1970, 80, early 80, yeah. I graduated 79, and I need to go to service in Army for 2 years. So after I returned from the Army service, I realized I cannot find job in Taiwan because no industry. And my elder brother or elder sister, they are all graduated from the Taiwan Normal University. So it's easy for them to, how do you say that, to become a high school teacher. But at that time, National Taiwan University, even though they are the top choice for the basic science, they cannot go to high school to become a teacher because you need to graduate from National Taiwan Normal University. So then I talked to my classmates, where are you going? It turned out to be they all went to overseas. So then I realized I need to go to overseas. So I moved to UC San Diego at that time.
I see.
And yeah, in UC San Diego, then the first time in the very beginning I joined the astrophysics, but then I realized in Taiwan there is also no astrophysics at that time. So I tried to choose one field between physics and fundamental science and something can be useful. And at that time it's a very good chance because in UCSD, the Center of Magnetic Recording Research, CNR, they just established. They recruit the student. So then I decided to switch my field. So I moved to the magnetic research at that time.
I see. Thanks so much for sharing with us. So I guess this is sort of your career research roadmap. You start from magnetics, and then you focus on micromagnetics actually at that time, and then move to nanomagnetics and more on spin charge interplay. But could you elaborate more on the micromagnetic study, perhaps?
Yeah. I think you have a very good summary. Actually, I probably changed the. Actually, it's not. I changed the field. Actually, it's the environment change. They move from the bulk, thin film, then 2D material, and then you need to follow the trend. But basically, actually, the fundamental, you need to have some fundamental expertise. So I stick on the magnetic all the time. Actually, magnetism. So yeah, for the micromagnetic, actually, the reason I started is because of actually a lot of time, UCSD, as I say, they have the CNR just established. Then 1 year later, they have the high performance supercomputing center also established in UCSD. The first Cray XMP48 was installed in UCSD. So my advisor say, hey, come on, go to use that. And before that, actually, I'm a theorist. So before that, actually, if you need to do every calculation, from scratch and on the paper. So you need to good on the math, such as special function. And magnetism at that time actually was a micromagnetic. Brown Jr., William Brown Jr. started, and then Aharoni and the people from Israel. They use a lot of Bessel function to calculate a lot of analytical result. And actually, I start from there, actually. And however, to use the analytical solution, usually you have limited. You can calculate only very ideal case and also probably a single particle situation. But when the high performance computing came out, Cray XMP48, my advisor actually in CNR was the Fredkin, and he asked me to use the machine to calculate the result. And
we have a image
Yeah,
for that computer here.
Yeah. And as you can see, that supercomputer actually at that time, just like the quantum computer now, a very big room, only one, something like, right now I say they are bamboo, something like bamboo, from the ground.
On the ground.
Yeah. But right now, actually, the super quantum computer is just like some stone hanging from the ceiling. But they're similar. It's very big. Not too many people can use that. I learned this actually for 3 months because they are almost machine language. It's not non-trivial. Actually, I attended school to learn how to use for 3 months. And then I started to use that to calculate the micromagnetic. And this figure actually is the first one I calculate, 8 by 8, stone-Wolf's particle. And the interact in between them are the dipolar interaction. And at that time, it's non-trivial because those 8 by 8 figure, I need to run on the Cray XMP48 for 1 week, of course, including the real clock waiting time. But anyway, after a week, I got a history diagram. And the result turned out to be very unrealistic, frankly say. Yeah, this one actually is probably the first paper I published with my advisor. As you can see, actually, I try to do as large as I can, and it is the biggest figure at that time I calculate, use the micromagnetic calculate. And the result turned out to be they usually will switch cluster. So they have a very clear step function came out. However, at that time, no experimental result can how do you say, compare with us. And they never see those very strange, reversal behavior. Yeah, so at that time, actually, they have one experiment group, Shelley Schultz group, and my classmate, Joe Smythe. So they decided use the state-of-art technology, e-beam lithography in IBM to make the particle array just like this. However, as you can see, a lot of state-of-art, the smallest particle is only in submicron. And their result never see my calculation result. So it's quite frustrating for me at that time. Because actually I think my calculation must be a certain problem. And because it never fit with the, the experiment result. However, actually at that time is the most advanced, numerical result. Then probably is one of the first paper, to study the micromagnetic calculation in hypermesh computing.
I see.
Yeah.
But I think nowadays that we can make like MRAM devices, devices in nanoscale. So your calculation back then should be much useful.
Yeah. However, actually, at the time, one thing is just remind me, the small arrow. All those small arrow, at the time, we don't have too many computer software. So I need to go to the how do you say that, the computer science to take one semester courses to learn how to draw the 3D dimensional projection on the screen. So then I write a subroutine and then call the subroutine to show the 3-dimensional arrow at that time. Back to 1983, probably 84, and I think it's very useful. But turn out to be right now, every student can easy to get a much advanced graphic actually.
Yes.
Yeah,
indeed.
here.
Yeah. Nowadays they use UNF or UberMac and all those platforms. They can plot it very easily.
Yeah.
So it's a very interesting journey, at least for your PhD study. And at that time, can you talk a little bit more about the during the 80s and what's the atmosphere for the society at that time, and especially in the U.S.?
Yeah, actually, I think 70 to 80 is a very big transition for magnetism. Actually, before 70, 80, probably the major is Bach. And people experiment only can study the Bach material. And about 80 actually came out e-beam lithography, and the MBE machine came out. First they applied to the semiconductor. Then during the early 80s they transited to the magnetism. However, in magnetism from 3-dimensional to 2-dimensional, they have some Hohenberg-Mervin theory claim that actually 2-dimensional material, they shouldn't have the spontaneous magnetization. And but however, at the time, actually, old experimentalists claim they already built the 2-dimensional material. But however, still observe the spontaneous magnetization. Then the question then came out, why is that? And so I actually was at that time. Shirley Shows actually came to me at that time. Hey, come on, can you calculate, since you have 1 by 1, can you calculate 1-dimensional thin film? And because we build the thin film, we still observe the spontaneous magnetization. But anyway, later on people know more actually on the fundamental physics, because all the film is not freestanding. And also they have the intrinsic uniaxial, probably because it's not simple spin. They have the internal structure. And so actually gradually learn, actually even 2-dimensional, is possibly because of the uniaxial anisotropy, some kind of localized anisotropy. You still will observe the spontaneous magnetization. But anyway, this is the book when first I read. This is a summary by the JAN. Actually, they have the magnetism beyond 90. They summarize the first book. Actually, I read the series on the older histories. They summarize all the progress on the magnetism before 1990. Then this is the magnetism beyond 2000. But after 2000, you never see this, because magnetism suddenly, like booming. They extend to every field.
Yeah.
And so it's not easy to use one book to summarize the 10-year progress. And but there is also another thing, probably is shown on the next slide. In the early 80s, Japan Magnetic Society was very advanced in the commercial product. Something like the magnetic recording. Actually, my PhD thesis is related to the perpendicular recording. Right now, really, you know, already applied on the most advanced material recording industry. But actually, my PhD thesis back to 1980 is really studying the perpendicular recording, and so the Japanese actually is very advanced on the magnetic commercial product. So that's actually another reason why UCSD tried to set up the Center for Magnetic Recording Research in UCSD. Is actually they try to join the industrial effort. So UCSD recruit 4 professors from industry directly, such as John Marlinson as our director center, you know, head is from MPAX. So they bring into the industry, you know, research topic. So change the attitude actually of the academic. And why they did it? Because at that time I heard actually the U.S. university and the industry try to understand how come Japan can be so advanced in commercial research, actually product research on the magnetism. It's that they have the very good system between university and the industry, something like this. So they try to mimic, you know, Japan's system to set up the first industry research center in UCSD. When I was a student, I have one interesting thing. I read a lot of Japanese journal because IEEE transaction actually Indeed has special journal. I think every month to translate the Japanese art journal from the Japan Magnetic Society into the English. And I think last for probably 10 years. And when I was student, I read almost every journal. So we learn a lot of perpendicular recording from that. Otherwise, actually, not too many articles related to perpendicular recording at that time in United States.
I see.
Yeah.
It's very interesting. This, I mean, reminds me of in the old days. I mean, people have to read like German papers.
Oh,
They want to study physics. Yeah, and
Yeah.
they have to translate those German papers into English as well. But this time, during the 80s, seems to be Japanese, and you have to read the translated version.
Yeah, times change. Actually, when I was undergraduate in National Taiwan University in the physics department, Germany is a required language for us.
Oh,
I learned
see.
2 years Germany.
Wow.
Because actually, as you say, all the library journal,
Yeah.
library the book, a lot of is in Germany. But at that time, they didn't ask you to study the Japanese. They only translate it into English.
I see. I see. It's a very interesting time, actually. And since you cover, you mentioned a lot of your, your times in the in micromagnetism and also perpendicular recording, and here you summarize this your research path. Can you share with us a little bit more about this complicated?
This is one of my slides when I give the, how do you say that, the presentation or introduction courses to the student, even for the general talk. What is the history for the spintronic? Actually, frank to say, I think I'm in a very lucky, period. Because my PhD started from 1983 to 1988. At that time, they have a lot of events that actually happen in the fundamental science or material side. In magnetism first, the niobium ion boron, submarine copper was occurred at that time. 1986, I think. Suddenly, the energy product jumped. And right now, become very useful in everywhere. But the lead material was identified by Japan, I think, 1985 or 86. Then the second thing is actually is the spintronic. The spintronic actually, because actually MBE just appeared, So AT&T used MBE to do the three-layer structure. They used the rare earth insulator and the rare earth. Then 1986, they identified the RKKY-like interaction between the rare earths. Then suddenly, super high temperature superconducting came out. so everybody moved to that. If you in 1987, you cannot imagine how people how crazy about that. how people crazy about. Everybody moved to that, and so nobody tried to do this. Well, even though it was identified 86 and 87, and probably only Grunberg and Everett, stick on that field. They moved to the 3D structure from 4F to 3D, because actually Grunberg and Everett, they are expertise on the 3D material. But when you change 3D, everything changes because transport behavior change. They are Itarian, electron. So suddenly they identify giant magnetic resistance. But in the very beginning, still nobody really pay attention because everybody was drawing attention to high TC. And I think Stuart Parkin actually do a lot of things. And he then pushed this one from the very low temperature, 4K I think, suddenly moved to the room temperature, then become very useful, in particular on the recording head and the sensor, and the later on, push to the other field. But anyway, the main change actually is that in between the magnetic layer, first the people use conductor, then insulator, then semiconductor, then superconductor, topology insulator. So suddenly, change to everything. Right now, I think ultramagnetic. But then they start a very, big family. So every 5 years, you have new things can be done. so it lasts for almost 40 years already, but still in progress. And a lot of things change and give people a lot of inspiration and the future hope. And in particular, industry find is really useful. If you compare with the superconductor, high temperature superconductor, probably niobium ion boron and the spintronic more impact than the high TC now. Yeah.
Yeah, so it's interesting because condensed matter physics typically jump between magnetism and superconductivity and back and forth.
Yeah, but anyway, you need to keep your pace, with the time change. I always advise, my student also is this. You need to have your own expertise, and also need to catch with the wave, and prepare yourself. And when the new wave comes, then you have the expertise, easy to catch up the wave, and the things will gradually change, and suddenly they have a jump. So if you go through the history of the spintronic, actually good learning period. People gradually move. Of course, this move also depends on the experimental instrument technology, such as when TNR came out. At the very beginning, it's very non-trivial experiment. I still remember that time when I just moved to Taiwan, I suggest my experimenters to do that. They say it's impossible. And right now, everybody can do that, yeah.
So since you mentioned, I'd like to switch gear a little bit about your transition from back in U.S. and then back to Taiwan, and what made you do that? And, was that a hard transition for you at that time?
Yeah, I think this is a tough question, and but I make it easy. Actually, yeah, when I was go to overseas, a lot of Taiwanese actually go to overseas, but not too many people move back.
That's right.
Yeah.
A lot of them stay there.
And I do make certain interview actually, because actually I studied magnetic recording. Actually, at that time is rising, industry in United States. So I still remember, I think 6 months before I graduate, I have one thing just occur in my mind. Parallel in New York. You know, Kodak and the Parallel. They are film industry. They use the nanoparticle, however, it's chemical nanoparticle, to make the film. But the digital camera gradually came out, so they know they need to transit. So the easy way for them to transit to the magnetic recording. So Kodak make a lot of very good research on the magnetic recording. They even have a very big research lab in UCSD. We interact with them a lot. However, they never transferred, so they disappeared. And the Parallel also, I still remember 6 months before I graduated, I got a phone call actually from the VP of Parallel. Say, we tried to initiate one magnetic recording group in Parallel. Can you join us? I say I still have 6 months to go. And I say maybe after I graduate we can discuss. But 2 months before I graduate, I got another phone call from Parallel. So they say their VP was laid off. so the whole project suspended. But anyway, I do interview with Applied Magnetic Corporation at that time in Santa Barbara on the recording head. But my specialty actually is the recording media, particular media at that time. But they tried to use the numerical to the recording head. So I went there for 2-day interview. It's very, I never know interview is so you need to talk to every group. Yeah. Not only to give a talk, you need to talk every group. And AMC at that time is very rich. I still remember their VP invited me, on the beach restaurant, open a bottle of wine at night, $200. At that time, 1 week for me, probably I spent only $30. But anyway, so I think, hey, it's a good life. Yeah. If I really stay in United States. But the main reason, for me to move back, one of the main reasons is that just about, I think 3 months before I graduate, I broke up with my girlfriend. So my mood was, so unstable. I think probably I should go back to Taiwan. So then I decided to go back to Taiwan. Yeah, it's not the other reason.
I see. So you came back here, but did you directly come to National Taiwan University, or you sort of have some detour before that?
Oh, this is also interesting, because actually I studied in UCSD. It's not prepared for the academic at that time. Actually, it's applied physics, and mainly actually interact with the industry people, because the CNR, environment, we interact with industrial engineer very often. So when I came back, I joined the ITRI at that time. I see. And 1988 September, I moved to ITRI. But when I go to ITRI, because I'm high performance numerical, computer numerical person. When I joined Taiwan at that time, suddenly I realized they don't have any advanced computer. I cannot do the numerical calculation in Taiwan. And then without those environmental, you really cannot contribute much, actually, yourself to the industry. And so National Taiwan University Physics Department Chairman at that time came to approach me, say, are you interested to move back to academic? Then I decided probably is a good chance. So I joined ITRI for only 6 months. Oh, okay. Then moved back to NTU the early 1989. Yeah. But right now, I'm not quite sure if this decision is right or wrong. The reason is following. When I was at ITRI, TSMC just started up.
Yeah.
And I saw the first factory.
Yeah, first fab.
Yeah, first fab, 6-inch, just next to us.
Yeah, yeah.
and people move the worker, move back and forth. And I talk to them. I say, what is your, just next to my office at that time. I talk to them, where are you working? They told me it's TSMC. I say, what is TSMC? If I didn't join NTU, probably I joined TSMC at the time. So you never know your decision.
Yeah. For those of you who don't know, I mean, ITRI is Industrial Technology Research Institute, and TSMC is one of the most successful spin-off. It became very successful, and I believe most of you know about TSMC these days. Yeah. So, so after you moved back, I guess that you started a lot of this education and also community activities. And so I want to switch gear a little bit to talk about the initiation of the IEEE Magnetic Society and the local activities here. Could you share with us?
Yeah, I just say I moved back to Taiwan 1988 and joined NTU 1989. As everyone know, actually Spintronics just started at that time. Actually in 1987, Ferd and Grunberg published that paper. So I probably is the first person to make an introduction of the Spintronics in Taiwan, actually also in China. So I give a lot of introduction lecture actually in around the Taiwan and China, and later on I gradually realized not too many people in Taiwan at that time to doing the thin film magnetism. They are all doing the bulk, hard magnetic, soft magnetic material, and not actually on the thin film materials. So Spintronics actually is beyond their knowledge at that time. So after I traveling around a lot to give the different introduction courses, then I gradually realized we probably should organize a certain, group effort to do something like that. So I because I come back from USA, so it's easy for me to access the United States, Magnetic Society, because when I was a graduate student, I joined the conference, Shuyan Conference, and Intermag, also almost every year for 2 conferences. So I knew a lot of people actually from IEEE. So then I realized probably we should initiate some kind of the IEEE activity in Taiwan. So first time I tried to, this occurred to me is because of the Intermag traveling around in European and Asia. Every 3 years go to European or Asia, 2 years in the United States. So every 6 years they will come to Asia once.
Yes.
And usually go to Japan. So I think probably we should try to, apply for this chance. So then I submit the proposal, and compete actually with Singapore at that time. I will not describe all the hustle or detail, but anyway, finally we got, and so we organized this one in here. And I think that since this was happened, we probably should also initiate the IEEE Magnetic chapter here. But not too many IEEE Magnetic members in here. You need to have a minimum membership.
Yeah.
I don't know how many, but you need to have a minimum membership. I forgot how many. But Taiwan at that time, I have 2 sectors. One is the Taipei sector, the other is Tainan sector. We don't have enough members within one sector. So then I talked to the chairman. I think the president of IEEE excited a lot of time. Is that possible to co-sponsor by 2 sectors? But not too many cases at that time. And so They say probably it's okay. They are not sure. But anyway, asked me to submit. So then I go to talk to the two sector chairmen, ask their endorse. Then we finally get enough member. So they initiate the IEEE Taiwan Magnetic Society. It's not belong to the Taipei sector or Tainan sector. It's a joint sponsor. So then we studied actually those activities in probably is one of the first magnet chapter, except in Japan. But later on, right now, in a lot of magnet chapter already appear in Asia. Yeah, but anyway, this one actually is we don't have too many researchers actually in Taiwan on magnetism to join the IEEE Magnet Society. But right now, the things change a lot. Yeah.
I see. So, as a final, remark or the conclusion, do you have any suggestions on, like, for the younger generations, like, to join the society and to work on something new, or what should they do? I mean,
okay.
in terms of like communicating or interacting with the IEEE society.
I think if you want to use the magnetism or magnetic, as your career, you need to join the society. You cannot do the things by yourself. You need to learn things from other people. Because actually right now, it's not like 100 years ago. You can study everything from yourself. One of my friends always told me, right now there is no small science. Everything is collaborated big science. And so the interaction and you get a lot of friends from international society is important because you knew the things change and easy for you to catch what you should do for the next wave. So I think the things still, just as I say, you need to have your own expertise. Such as at that time I know my own expertise is the fundamental mathematics applied on the physics. I'm good on that. And then when the things come, you need to advise your expertise a little bit to catch the spirit of the new things and modify and change. However, you still need to keep your curiosity. I think the curiosity is the most important motivation for you to get to learn and know the new things. Without the curiosity, you cannot do anything. So, such as actually I recently changed to the quantum computing. I think the future magnetism also will move to the quantum computing because spin is a natural quantum qubit. And but we still didn't know how to, really manipulate the spin as an entangled qubit. And but gradually, I think we will know. In particular, I think the spintronic probably will provide another, even though already been proposed, but we still cannot very easy to control that, the pure spin current. And if all those things can be successfully achieved, I think the whole things will change. So actually, I think it's a good timing for the new researcher, in particular for the younger generation.
Okay, thanks Professor Zhang for very nice, these very nice historical, coverage, and also these comments and remarks for our younger generation. So with that, I want to conclude this interview, and I'd like to thank Professor Zhang again. And I'd also like to thank the sponsorship from IEEE Magnetic Society to give us this opportunity to interact.
Okay.
Okay.
Thank you.
Thank you so much.
Yeah, thank you.